So curves and parametric curves. So what is a curve? A curve in Rn is a set of points, C, called C for curve, right? That's given by what? It's given by some vector valued function R, evaluated where for all parameter values T, where T is chosen to live in some domain, right? And this domain is a subset of the real numbers, right? So some set of real numbers, that's what T is being pulled from. Um, and then R maps each real number to a n tuple of real numbers, right? So that's what's defining a curve, right? And this, for all the fancy notation here. This is something that you've seen before, at least you've seen examples of this before. Probably the most famous parametric curve. Oh, and also I should say, this R and this D, right? This is called the parameterization of C, right? This is so a choice of R, of vector R, and T, right? This is a parameterization of C, right? This is and not just D, but the whole thing, right? So the domain along with the function R, right? So yes, I claim this is something very familiar. If you take n equal to 2, right? If you take D equal to the interval 0 to 2 pi, right? Closed on one side, open on the other, and take R equal to cosine t sine t, right? Then this is something incredibly familiar. This is the unit circle, right? So this is right. This is the unit circle in the plane. So here we're opening it up to kind of any dimension n, right? N can be any value. We're opening it up to any domain D. We're opening it up to any vector valued function R, right? But this is something very familiar, at least in this case, right? We've seen an example of a parametric curve and a parameterization of that curve, right, in trig, right? So what's the idea here? The idea is if you picked this location right here, this would be the point R of 0, right? And R of 0 would be the point cosine of 0, comma, sine of 0, right? If you picked this would be R of pi over 4, would give you the point root 2 over 2, comma, root 2 over 2, and so on, right? And then it would go all the way around the circle, right? Over here would be the point R of pi, which would give you negative 1, comma, 0, and so on, right? So it starts here at this point, it goes around and around, and then it stops at that point again, right? So this is our unit circle. All right. Um, another example of a Here's another example of a parametric curve. So if you take a line in 3 dimensions, right? This is a perfectly good parametric curve. So it doesn't have to literally curve like how we tend to use the word curve colloquially in English, right? It can be a straight line, right? It just has to be able to be described in this sort of one-dimensional parameter kind of fashion, right? So this is a perfectly good parametric curve. right? And what would this be? This would be, here's x, y, and z. Here's the point. This is starting at the point 1, 0, 0, right? If I plug in, and here I'm just using L instead of R, but it's the same idea, right? And then from there, I'd go up to L of 1. I'd go over 1 unit, right? And then up 1 unit in the z. There's my direction vector, right? Is 1, 1, 1 here. And I would keep doing this, right? This would be L of 1, L of 2, and so on. Right down here, you'd have L of -1, should be 0, -1, -1, and so on. So there's another, right? Now, one thing to note is this set C, you can parameterize it lots of different ways, right? So you can say this is a parameterization of C, but here's another parameterization of exactly that same curve C. So instead of L, let's call this, or here, let's call this L1. You could do L2, right? And let's say on this L2, I'm going to do T -1 plus T and -1 plus T, where T is in the reals. This is another parameterization of exactly the same line, right? If I switch this to blue, right? So what makes this parameterization different? What's the starting point? This is the starting point, right? So this would be L2 of 0, right? See, so this parameterization has this as its initial point, right? But then has the same direction vector. It goes like this, right? So then this point would be L2 of 1. This point would be L2 of 2, and so on, right? So you can actually have infinitely many different parameterizations of the same curve, right? Um, just like on the unit circle, right? Here, we did this one particular way, but if you wanted a different parameterization of the unit circle, you're going to get the same points, but at different t values, right? If you say, see, I could do this. I could do R2 of t. I could do cosine of 2t, sine of 2t, right? Where then t only has to go from 0 to pi, right? Because um, it goes twice as fast, basically, right? So a lot of the time we consider t to be time, right? So this would be sort of a particle this would be considered to be a particle that completes the circle in half the time as this one, right? This one took 2 pi seconds to move around the circle, and the second one, R2, only took pi seconds to move around the circle, right? So this is something that's nice about parametric curves. You have a lot of freedom to describe motion this way, right? They're very, very common for describing motion. Okay, so those are two examples, right? Simple examples of line and a circle, right, of parametric curves. But you can really have any formula you like in R of t, right? And here I did one example in 2 dimensions, one example in 3 dimensions, but you could do this in absolutely any dimension. So, all right. So let's look at some calculus on parametric curves. So let's look at the for all of this, we do a bunch of definitions, and let's say for all of this, we're given a we're going to have the same notation for all this. So we're going to have this parametric curve C given by this function R of t, where t is in some domain, right? And so here we have, so the first thing we want to define is the velocity And here I'm gonna define all of this in 2D. But you can actually do it in any dimension. Um, all of these formulas are the same if you're in 3 dimensions, 4 dimensions. You just keep adding more terms, right? So the velocity, what velocity is it's just the component-wise derivative. So you see whatever formula is in the x-coordinate and take its ordinary Calc 1 style derivative. See what formula is in the y component and take its ordinary Calc 1 style derivative. So this is the velocity. You're just measuring the rate of change on each component and then building a vector out of that. All right, so this is the velocity. This leads quickly to another definition. So sometimes people call it the unit tangent vector. Sometimes people don't say unit, they just say tangent vector. This is the velocity vector divided by the speed. So what's the speed? Speed is the magnitude of the velocity vector. Right? So you may have seen these ideas in, say, even in just one dimensional motion, right? Say in a physics course. Say you're talking about the velocity of, say, just a car moving back and forth along a road, right? The velocity of the car could be positive 10 miles an hour or negative 10 miles an hour. But if you say what's the speed of the car, in either case, you would just say 10 miles an hour, right? You would take the absolute value. Same thing here, right? So here we're possibly in higher dimensions, but same idea. You can have a velocity vector which would have direction and magnitude, then the speed of that velocity vector is the magnitude of that velocity vector. That's what we call speed, right? Okay, so this tangent vector, what is this doing? It's velocity divided by speed, right? So this is a unit vector, right? So what this is doing is it's stripping away just the direction of the velocity vector, right? And ignoring the magnitude. You've divided it by its own magnitude, right? So this is essentially, you could think of the tangent vector or the unit tangent vector as it's the direction the particle is traveling. Right, without worrying about how quickly, right? It's just showing you the direction. So I think a good example of this is if you look at the 2 parameterizations that we gave of the unit circle, right? So you can say this is the unit circle, right? And this, just like up above, is also the unit circle, right? These are both perfectly good descriptions of the unit circle. But suppose I said in each case, what is the velocity, speed, and tangent at, let's say, the point root 2 over 2 comma root 2 over 2, right? So right at that point, I would ask, what is the velocity, what is the speed, and what is the tangent, right? So here's the idea is um, so R2 should be traveling faster than R1 because it completes the same loop, right? But in half the time. So I would think that the velocity should be a bigger vector. The speed should be larger for R2, right? But the tangent vector should be the same because the tangent vector should just show what direction is being traveled and not really care how fast, right? So that's the idea here. The tangent vector, at least up to a sign, should be independent of the parameterization that you choose. The tangent vector is just property of C, at least up to a sign, right? As opposed to velocity and speed can depend on how you parameterize, right? So this is where the tangent vector is really nice, is it's sort of a property of the curve itself and not a property of the parameterization. So, all right, so let's look at this. So here, what would I have if I did this for R1? Right, let's do R1 prime. It would be negative sine of t cosine t. So R1 prime at pi over 4, right? This would be minus root 2 over 2, root 2 over 2, right? There's our velocity vector at that point, right? So it would look like this. So this vector would be R1 prime of pi over 4. Okay. Versus, let's do this one in blue, right? If I did R2 prime of t, now I get some chain rule. So it's a very similar calculation, except I have chain rule here. Right, so now this becomes negative root 2 and root 2, right? And why am I doing pi over 8 as my t value? Well, because this location right here, this is R1 of pi over 4, right? But it's R2 of pi over 8. Right? To get the x and y coordinates to be root 2 over 2. To R1, you have to plug in pi over 4 for t, but to R2, you only have to plug in pi over 8 for t. So, okay. So see, this is a vector. It's essentially, for R2, it's essentially the same vector, but it's going to be twice as long. Right? That's going to be R2 prime of pi over 8. Right? So the velocity vector for the second parameterization is twice as big. Right? And if you do the speed calculations, this shows it, right? If you say what is speed for R1 at that point, right? Speed here is going to be sum of squares, right? Square root of the sum of squares. So the speed there is 1, but the speed here is going to be, again, the square root of the sum of squares. That's going to be 2, right? So there we have our two different speeds, right? One for R1, one for R2. But the tangent vectors will be the same here, right? Because what happens in the case of the tangent vector, if I do the tangent vector for R1, I'm doing R1 over the magnitude of R1. Sorry, R1 prime over the magnitude of R1 prime, right? The velocity divided by the speed. So what does this become? Well, I have, you could work it out just at that point, but I'm going to show it in general for any t, right? So this would be again the velocity divided by the speed. Well, here you can see the speed is just 1 by the Pythagorean theorem, right? I get a sine squared plus cosine squared in the bottom. As opposed to if I did it for the second curve, or this, well, it's the same curve, but the second parameterization. Right, there's our velocity divided by speed. And in this case, so the velocity has double the magnitude, but that means the speed is twice as big too, right? So see now down here, I could factor out a 4. So I get 4 times sine squared plus cosine squared. And the sine squared plus cosine squared goes away. That's just 1. Square root of 4 is 2. See, so now I get -2 sine t over 2 cosine t, or 2t, right? Divided by 2. That's, you could think of this as scalar multiplication, right? Think of this as, the scalar 1/2 times all of that, right? See, so the tangent vector comes out exactly the same for these two parameterizations, right? So there's t1 and t2. Right, basically this velocity vector, the r1 velocity vector, was already unit length, right? So this was already equal to t1 of pi over 4. That already was the tangent vector, but this blue one, this was magnitude of 2, right? So the dividing by the speed would shrink it down to be just unit length, right? And that would be your t2 of pi over 8, right? So the r1 prime didn't get shrunk at all. It was already magnitude 1. The r2 prime was double the magnitude, so that got shrunk by a factor of 2 down to this tangent vector t2. Okay, there we go. So there we have 2 examples of calculating tangent vectors, right? Just to warn you, they're usually messier than this. This is a pretty clean one because that cosine squared plus sine squared cleans up so nice, right? A lot of the time you have in your tangent vector, that square root isn't going to disappear, right? And you'll have that just as part of your answer for the tangent vector. So there's nothing wrong with that mathematically, just warning you. So all right, so that's tangent vector. Then there's a related definition, of course, to tangent vector, which is that a parameterization is called smooth. Wherever speed is non-zero, right? So like if you notice these 2 parameterizations that we looked at, these were smooth everywhere because they're always speed 1 or always speed 2, right? So they always had non-zero speed, right? But you can have parameterizations where the speed does actually go to zero at some point. Um, this is often, where you get a um, cusp or a corner, right? So often a cusp or a corner has speed zero. So that's, sort of visually what is happening when you have a point that's not smooth. So I think that's why they call it not smooth, because you could poke your finger on it. Um, so that's a related definition. It Most of the time in practice working with these, it doesn't come up a lot, but sometimes you need to be careful about smoothness, especially just in the statement of a theorem. Um, so, all right. So that we won't focus on too much, but it's a good word to keep in mind. Because note that um, the tangent vector does not exist, right? When it's not smooth, right? Because the tangent vector, that's the denominator, right? See, speed is the denominator of the tangent vector, right? So if that's zero, um, then you can't calculate the tangent vector. And I mean, this lines up with how maybe in Calc 1, you would say like at a cusp, there's no tangent line, right? The tangent line is undefined. It's the same idea here, right? There's no tangent vector at a corner or a cusp, which is typically where speed would go to zero. Okay, so this is then our next definition, um, normal vector. So the normal vector, and again, sometimes people say unit normal vector, and sometimes they just say unit. Sometimes they just say normal vector. This is the direction in which the tangent vector is changing. Okay, so that's a nice wordy description of it. What is it as a formula? So it's, you take the change in the tangent vector, t prime, but then you see here, I just want the direction in which it's changing, not the speed at which it's changing. So you do the same trick as before. You divide that rate of change by its own magnitude to get something that's guaranteed to be unit length, right? So this is the direction in which the tangent vector is changing. Um, so good visual for this, I think, is the circle. I think this is probably the best thing to do is jump right to an example. Um, so again, if we look at that circle, right? If you think about, right, from this point, and let's say we're back at the kind of the basic parameterization, that what I was calling arm1 up there, but I'll call it R now. Um, if you think about the tangent vector here that we calculated, right? So this was the tangent vector at pi over 4. And then you think of the tangent vector an instant later. So let's do, I don't know, say purple, right? So a small, very small unit in time later, right? You can ask, in what direction is the tangent vector changing, right? And so you could say from here, where is it going really? But it's falling down, right? The y coordinate of the tangent vector is decreasing, right? And it's also going to the left. So that's the change of the tangent vector is going down and to the left, right? As you go from the black point to the purple point, the tangent vector goes down and to the left. Okay, so now graph that from here. Graph down and to the left, and also graph it as magnitude 1, right? This is going to be a unit vector because I took a vector and I divided it by its own magnitude, right? So go, right, draw down and to the left. That's going to be your normal vector, right? That's going to be the normal vector at pi over 4. And here I just sort of sketched this visually, but let's actually calculate it and show that it's exactly that. Right? So we already had from up above, we already had that r prime was negative sine of t cosine t, right? We already had that t then was actually the same thing in this case, right? Because we divided it by speed. But that speed was just 1, right? So in this case, tangent actually equaled velocity. Tangent vector equaled velocity vector. And then from here, we could take t prime, which sometimes, by the way, sometimes this is called angular velocity. We're not going to focus too much on that here, but you might hear that in physics sometimes. So t prime, what is that going to be? Right, just differentiate, right? How you differentiate a vector, just differentiate each component. So do your derivatives here, and then we could do our angular speed, right? Is what? Well, this again is 1, right? Because this is again going to be cosine squared plus sine squared. Is 1. So what is the normal vector? The normal vector here is t prime over magnitude t prime. Right, so negative cosine t, negative sine t. Right, that's our normal vector. And if you look at this at pi over 4, what would that be? At pi over 4 then, that would be negative root 2 over 2, negative root 2 over 2, just like I graphed, down and to the left, right? If you actually plug in that pi over 4. So there we go. There's an example of tangent and normal, right? You have the tangent vector shows you what direction the particle is traveling. The normal vector shows you what direction is the direction changing in, right? All right, there we go. So there's our definitions of there's some sort of basic examples, circles and lines of curves in 2 and 3 dimensions, right? The definition of velocity, tangent, normal. So yeah, these are some key vector value function terms that we'll use as we go along. A lot more to come.